Alright folks, welcome back to the Infodump, the series where I do a deep but not necessarily scholarly dive into a particular topic. Today we are of course continuing with our initial topic of physics, and last time we talked specifically about the physics of chemistry and how the mechanics behind electrons and protons and all that allow atoms to join together to create, well, molecules. That's what chemistry is all about, after all. So we touched on a little bit. Now, one thing that I feel like I should cover real quick before I get into this week's, just something I forgot to mention last week, is that the chemical reactions that happen to, change around what molecules are there fall just about always into one of two categories: endothermic or exothermic. If you know your Latin, you'll recognize that as meaning internal heat and external heat. Endo, internal, exo, external. Internal, external, endo, exo. It's kind of in the name, folks. Anyway, essentially what that defines is where the energy is going or coming from. Remember, heat is sort of the core form of entropy. It's also one of the most common forms of energy. So when a reaction is absorbing that energy in order to form bonds, well, then the process of breaking those bonds is going to be a reaction that releases or generates to, uninformed observer, that heat. It's not so much removing and then creating heat, it's rather storing heat in the form of another kind of energy, specifically what we call chemical energy. Now, of course, that does not necessarily mean that all exothermic reactions are the reverse process of an endothermic reaction. Rather, it just means that all endothermic reactions, when reversed, will be very likely to be exothermic reactions. I am not a chemist. I do not have full and complete knowledge of every single reaction out there and whether it's exothermic or endothermic. That's not part of my wheelhouse. I am an armchair physicist at best, and this is just one little bit that I wanted to touch on. So, with that done, let's actually get into this week's topic. So today, we are going to be talking about something that is a little bit bigger in some ways than individual atoms and molecules, but is still very much relevant, and that is classical mechanics, classical physics. That's going to be multiple videos. For now, really, we're going to talk about motion, because that is where it really all gets started. See, motion, in any sense, is simply movement in space over time. That is, in fact, quite literally how we calculate something's speed: change in distance over change in time. Of course, when you factor in the fact that space-time is a wibbly-wobbly mess, things get a bit more complicated than that. But broadly speaking, once you actually correct for all of those variables and relativistics and all of that, well, what you're left with is movement in space divided by movement in time. And that can be a bit of a wonky concept to wrap your head around at first, but the more you think about it, the more sense it makes. So if you feel kind of lost, just go do some basic thought experiments, like come up with some thought experiments for yourself, or if you're feeling particularly uncreative, just Google basic physics thought experiments. That is one of the best ways to enhance your understanding. Einstein, of course, came up with the theories of relativity based on thought experiments. Of course, don't let thought experiments be your only guide. Obviously, that is what Aristotle did wrong, fucking famously on this show. he never did an actual experiment. He just kept it in his dumbass head and let his powers of persuasion convince everyone that he was right when he was basically always wrong. Anyway, if you have a good sense of what I mean when I say movement in space divided by movement in time, great. That is how we understand and calculate speed. Of course, movement in time is something that we generally experience pretty uniformly, even when we are in a situation of, well, time dilation or time distortion. We still personally perceive time as moving at the same rate. In fact, just the fact that we think of time as an external thing that is moving, rather than us moving through time, kind of goes to show how sort of rigidly locked in we are to the way that we experience it. And of course, there's nothing we can really do, as far as we're aware, to change our perception of time, change from the way that we experience things, how it works. Of course, from an external perspective, say being in a gravity well, or being very high velocity will change the way that time flows, or rather the way that we move in time. But because of the way that relativity works, there is also a corresponding change in the way that space moves, or that we move through space, to account for that change in time. So that even if you are in a greatly shifted space-time frame, you will still perceive things as having the same speed through space and time that someone in a completely different reference frame will perceive. That is the namesake for relativity. Just as Galileo realized that a ball thrown by someone moving on a boat would look like it's stationary to an external observer, but would look like it's moving away to the person who threw it. Well, when you compare the relative speed of the boat and the ball, it's always going to be the same. The ball is always moving the same speed relative to the boat, or the boat moving that speed relative to the ball. The same way, by more modern concepts of relativity, sorry, bumped the mic a little, more modern concepts of relativity, the different inertial reference frames are really what we look at, and what we see is, no matter what, there's always constant movement. It might not always be in the same direction, hence why we generally say constant speed instead of constant velocity. It might not even seem like it's constant speed when we're only looking at 3 dimensions, but once we look at 4, yep, there we go, makes sense, it all works, the physics check out, etc., etc. And, well, that is sort of baseline knowledge that I want you all to have going into this, because that is what we're talking about, right? We're talking not about how we see things move, but rather how they actually move. Because, as always, our perceptions are fundamentally incomplete. We can only see the macroscopic level. We only really have a sense intuitively and instinctively for how things are moving in 3 dimensions, and so we have to use that wonder of evolution, the human intellect, to puzzle out everything else. Because, holy shit, it's not obvious. At least not unless you have a grounding in the science and the understanding of how all this shit works. Which, I mean, part of the reason I am making this series is to give more people that baseline understanding, more people that, sense of how the world works and how physics operates. I'll go into that more at a later date, but suffice to say, I find far too many people acting as though physics is some unknowable, mysterious, almost sort of like occult type of thing, when no, it's really just yes, at its core it's a bunch of numbers and whatnot, but once you boil it down to a sort of more layman-friendly level, or layperson-friendly level rather, you can fairly easily understand it without all of the messy numbers and complicated stuff, and just look at it and say, okay, I understand this concept, and I see how these two interact with each other. So, that little tangent aside, this is where we're going to really get to stuff interacting with other stuff, both literally and conceptually, if you understand my meaning. It's fine if you don't, I'm not even sure I understand it myself. Let's just get into it. So, when it comes down to it, movement, like I said, is, well, movement through space divided by movement through time, as we understand it. But it is essentially an object going from one point to another point. It's a bit weird to talk about movement in time purely because our understanding is so grounded in our movement through time. If I try to convey the concept of movement through time, I really can't do it without some sort of time-squared mental imagery to try and reconcile all of that. And I am not going to try and fix any of that right now. Honestly, it is something that I find very frustrating, but I don't have any real solutions for it. I think that's something that, generations upon generations of scholarship and linguistic sharpening and whatnot are going to eventually iron out. But for now, we don't really have a concept for movement separated from time, which is why I'm only going to be talking about movement in space, because, well, movement in time is kind of an assumed constant. It's how we experience the world. And we can't divorce ourselves from that, at least not easily. So, when we talk about movement in space, we generally think of it as an object having a particular amount of kinetic energy. That is to say, the energy that is causing it to move from one point to another. In a pure, perfect vacuum, an object with a given amount of kinetic energy will travel at its speed indefinitely. That is one of Newton's laws of motion. An object in motion will stay in motion unless acted upon by an outside force. Of course, we live in a gravity well on a planet with an atmosphere, so anything moving on Earth has to contend both with air resistance, or drag as it's more commonly known, as well as the planet's gravitational acceleration, pulling it downward. And of course, if it's moving along the ground, it has to contend with friction with, well, the ground, or whatever other surface it's moving on. We can get damn close to a frictionless surface, but no truly frictionless surfaces exist. There is always going to be at least an infinitesimal amount of friction there. Just like, no matter how far out into the cosmic void you get, there is still an infinitesimal level of gravity. Because, yes, the inverse square law is a thing, but just because you are a quadrillion miles away from gravity, that doesn't mean you're feeling no gravity. It means you're feeling that gravity multiplied by 1 over a quadrillion squared. So, yeah, basically divide the gravity by a 1 followed by far too many zeros. It's still there. It's infinitesimal, yes, but it's there. And when you're dealing with very large numbers, it becomes very, very apparent. Unless you're rounding, in which case, yeah, fuck that. That is why we round, in part, to get all of those nasty tiny little numbers and variables that we can't otherwise account for, because the world is imperfect, out. That, and to make things easy and simple on ourselves, I mean, yes, you could memorize pi to a billion digits, or you could just remember that it's 3.14159, etc. And those 5 digits will usually be all you really need. Well, 6 digits, 5 past the decimal point. Either way, 6 significant figures is usually more than scientists work with. It's about double. And when we're working with macroscopic objects, 3 is basically always the standard. You can get a lot more leeway working with macroscopic stuff because, well, I should say macroscopic but not planetary. But working with macroscopic, non-planetary levels of stuff, you can round to anywhere really between 3 and 9, and you'll basically have the same rough degree of precision. It won't be more significant figures than you need, and it won't be less. Anywhere in that range is pretty comfortable. Also, since you're only dealing with that many significant figures, when you're dealing with macroscopic but not planetary stuff, usually there's not a ton of calculations and computations you have to run, unless you're trying to make it relate to either the quantum stuff or the astrophysical stuff. And if you're doing either of those, then you have far fewer significant figures because you are, well, dealing with a lot more calculations and computations, and the more times you have to run through 6, 7, even 9 significant figures, the longer all of that takes, exponentially so. So it's best to just hedge your bets on the least necessary precision. That way, yeah, sure, you'll be off by a little bit, but unless you're trying to land a fucking rover on Mars, a little bit doesn't matter. And if you're trying to land a rover on Mars, units are more important than the number of significant figures. As we fucking found out! I still can't believe that there was an actual incident where some dumbass idiot didn't ask, wait, is this imperial or metric? And fucked an entire rover mission. Like, come on, man. Anyway, with all that said, that should give you a bit more grounding about, even though I said we're not going to be using a lot of numbers here, it should give you a bit of grounding as for how important the numbers are, which is not super, but if you want to be precise and accurate, pretty important. Anyway, motion for 3 dimensions can generally be simplified into a path. That path, while not inherently based on time, is very strongly connected to time. It is the point-to-point, essentially, measurement of where something is at each point in time, plotted out as a graph. Which, yes, is confusing, but that's kind of just how it ends up being. Anytime that you try and conceptualize beyond the 3 dimensions that we are used to thinking in, your brain starts twisting and bending and trying to turn itself into a hypercube to try and process that 4th dimension, which usually doesn't go well because, brains aren't meant for that. We're really good at figuring stuff out in 3 dimensions. I mean, we evolved by throwing things, so we have this innate knack for projectile physics, particularly in our heads. And trying to use that innate knack to try and calculate stuff that's more complicated than that is kind of a bad idea. So, suffice to say, motion in 4 dimensions is basically just motion in 3 dimensions with time. And we don't want to think about that, so we won't. Motion in 3 dimensions is usually cached, if you will, in the concept of there also being motion in the 4th dimension, which is how we know that there is motion happening at all. That is why you usually do not see 3-dimensional motion plotted out on a graph, because it would need to be a 4-dimensional graph. Instead, you'll usually get 2-dimensional motion plotted out on a 3-dimensional graph, or, if you are really lucky, you will have 2 or 3-dimensional motion without any backtracking or weirdness plotted out on a 2 or 3-dimensional graph. So if you have, say, a car that goes straight and then turns, looking at that in 3 dimensions, you would have a constant velocity in 1 dimension to represent time, and then it has a line going in a constant velocity in space, and then it turns, so it moves in one of the other directions that is in the unaccounted for dimension. So it moves at a constant rate in time, it's moving at a constant rate in space in one of the dimensions, and then it gradually curves to be moving at a constant rate in space in another dimension. Or you can just say fuck time, we don't care, and you can plot it out on a 2-dimensional piece of paper, which I realize now that I'm actually reading that is a bit dumb and redundant, but whatever. You can plot it out on 2 dimensions by saying, okay, we're just going to say, yeah, there was no backtracking here and it moved at a constant rate. So then, all you have is basically just a trace of the path that it took through space. You don't need to worry about time or anything like that. That's usually how we do things. We assume a constant rate based on the average rate. Because fuck time. Fuck 3-dimensional graphs. Fuck 4-dimensional graphs. We just want the simplest thing possible, and so the simplest thing possible we take. The next key thing about motion is to understand what exactly kinetic energy is. And for lack of a better understanding or term, it is the energy that is propelling the object. Or more accurately, it is the energy bound up within that object's movement. Because energy generally isn't free per se, it's always bound in something. In the case of kinetic energy, it is bound in movement. Heat often manifests as random kinetic energy. That's why, or rather how, heat is a form of entropy. It is chaotic kinetic energy. Now, when that kinetic energy is nice and orderly, something will be moving in a given direction, typically at a constant rate. The rate of change in kinetic energy is what we would generally call a force. That is to say, something is adding more kinetic energy or taking kinetic energy out. The difficulty being it's not necessarily always in the same direction or opposite direction of the current movement, meaning that it gets a little messy when we think of kinetic energy, and specifically in the context of velocity. This is one of the places where our positive and negative situation for mathematics kind of starts to break down, and we start feeling like we actually need 6 signs. One for positive and two for positive and negative in each dimension, basically. Given how messy that sort of thing tends to be, it shouldn't be all that surprising that we usually only look at velocity in a given direction at any time. We couch velocity as being either positive or negative, depending on the way that we want to frame things. When we want just how fast something's going, period, that's where we pull out speed. Now, force is usually measured as positive or negative when comparing it to velocity. And the amount of energy in something, the amount of kinetic energy, is based on the square of the velocity, which means that whether the velocity is positive or negative doesn't matter. It also means that the more kinetic energy you put into something, the faster it'll go, yes, but with diminishing returns. This is part of why it's really tough to get things going super fast. When you have something going at a high speed, it takes exponentially more energy to make it go faster than it would to get something to go a little faster. This is part of why, when you are accelerating in your car, you have to press down harder and harder on the accelerator to make it go faster and faster. Yes, some amount of it is drag from the air, but a bigger part of it, far bigger, is simply the fact that you need to put exponentially more energy into something in order to get the same increase in speed out of it. If you're trying to go from 0 units of speed to 1 unit of speed on something that weighs 1 unit of mass, then you only need to put in 1 unit of kinetic energy. But if you're instead trying to make it go from 1 to 2 units of speed, you need 3 more units of kinetic energy. And the problem just gets worse from there. Essentially, what you end up with is a sort of upward spiral, in a sense, of how much energy you need to get something to go fast. That is also part of why high-velocity weapons are so incredibly dangerous. Even a tiny little bullet going faster than the speed of sound has more kinetic energy in it than a wrecking ball going about 100 miles an hour. Yeah, the wrecking ball will impart its force more destructively most of the time, but that bullet will shred right through just about anything and keep on going. A little bit of a healthy reminder. That's also where the infamous rods from God super weapon idea comes in. You can just have a ton of kinetic energy in this thing, and when it hits the ground, you're delivering so much energy you might as well have set off a massive bomb there. Because hey, it works for asteroids, why won't it work for us? And the answer is because it's impossible to aim. But, you know, who needs to aim in all-out warfare? Anyway, I think I've made my point on that. So that is where I am going to call it for this week's episode of the Infodump. Thank you all very much for watching or listening, and I will see you all next time.